All right. Hello, everyone. So our project is called MLDL. It's basically multi-layer data provenance and federated learning for securing scientific AI pipelines. And in our goal in this project is to basically build an end-to-end integrity, provenance, and authenticity for scientific AI data sets and workflow. So let me start with why this matters. So as we know that genomics, climate, or other kind of sciences now depend largely on distributed data sets, and these data sets are really powerful, but they are also vulnerable to tampering, poisoning, or unauthorized access, or even some simple mistakes. So the idea is that if we cannot verify where the data is coming from and how it is processed, then the downstream results that you have become questionable. So our aim here is to build a provenance infrastructure that tracks the data sets full life cycle. So that the researcher or the domain experts or domain scientists gain transparency and accountability in these AI-driven workflows. As you know that in the system security research community, we have built such provenance-based systems for traditional computing paradigms. And our goal here is to tailor these, this so much work that previously has been done and take that work and apply those simple, those techniques and for scientific workflows. Now, what actually we are trying to build, so there are three thrusts in this project. The first one basically is to capture the provenance at different layers. So we have three different layers. The first one is the hardware or the instrument layer. So the idea is that in this layer we can capture the conditions and configurations from different sensors. And in this case, each record that we collect will be signed and stored in a tamper-evident format. In fact, we have an upcoming paper at ACM-CCS, which we are presenting next month, where we show that it is possible to efficiently collect such kind of records in a tamper-evident manner. Then the second layer we have is the application layer where this scientific workflow is running. And our goal here is to instrument these AI frameworks like PyTorch or TensorFlow so that we can keep track of the pre-processing choices and the environments they were in and what were the key training steps that took place. And then finally, we have the operating system layer where we will trace the workflow that actually ran, like the process start, container context, and how the jobs were scheduled. So we take all this provenance from different layers, combine them into this unified provenance graph or UPG. And this UPG will basically represents like entities like models and their configuration, and then the what kind of activities like that were performed, such as like pre-processing or training. Um, and uh, and then we have a backend which will basically try to store and ingest this graph, and then it will allow this domain experts to sort of search or query how, what, and when on scientific data sets. And if they need to know that why model change or why where this data is coming from, or if there is some sort of suspicious file, they can ask this question from the UPG, and then the UPG can answer that question. And then the final thrust that we have is basically to detect any sort of integrity issues collaboratively. So we will train a federated graph model with multiple organizations and to detect any anomalies without actually exporting or revealing the raw data sets. And then also we have a plan to, because these systems will be used by domain scientists and they might not have knowledge of graph query languages, our goal here is to build some sort of AI powered assistant that can take these natural language, plain English questions and turn them into exact graph queries so that domain experts can trace the causes without learning the query language. Now, who benefits from this? Like I mentioned, by building this framework, the scientists can get credible lineage for their results. The HPC and data platform operators see where their pipeline sort of drifted or broke. Incident response teams can localize the compromise locally by querying the graph. And this apply across all the different scientific workflows that we have for, like, for example, genomics or climate, while preserving the privacy through our federated learning model. So in this case, we have two main risks that comes to our mind. First is the visibility gap at the hardware level. As we know, it might not be straightforward to collect information from sensors sometimes. And the second risk we would have probably is related to high provenance collection overhead, right? So but we plan to use like efficient tracing or some sort of hierarchical storage so that the system stays practical even with these high overheads. How do we plan to sort of evaluate our system? So we will run real scientific workflows from NCBI genomics, or we also have data set from UVA climate, and we will track the sort of like the clear metrics for checking if our system is working or not by calculating the precision and recall along with the provenance coverage and also the cryptographic overhead that we add. And just to talk a little bit about the data sharing and requirements. So in this case, we plan to share the scientific data sets with the complete provenance that we collect. Also, the system that we are building, basically the application instruments that we add along with the kernel level traces that we are developing. Similarly, the federated learning framework with the differential privacy that we are developing, all those kind of things we plan to release. That's all.
All right, excellent. So I think this is, in terms of data, again, some data sets, not data set heavy. Well, one second, I'll do one question.
Yes, sure.
Yeah. Actually, go ahead. Yeah.
Oh no, it's very interesting as well about the provenance. I work on provenance, but not from the security point of view. I was wondering if you can elaborate a little bit about the representation of the data, because I can imagine they're quite heterogeneous and diverse. And the other one is how the storage, whether there is a continuous storage of the information, the provenance data, and in that case, how do you manage the aspect of cost and overhead of the storage process?
Yes. So those are really, really great questions. So to answer your first question regarding the presentation, so we thought about that a lot, and what we realize is that because there is a standard, the W3C OPM standard, we are planning to sort of use that ontology and to just extend that so that people can easily understand, because there is a lot of knowledge base out there for that standard. Regarding the second question of graph storage, yes. So there has been a lot of work in the research community where they have been developing efficient compression for these graphs and how to sort of have some sort of hierarchical storage so that you can quickly search the data which is in the sort of like a hotspot. So all those kind of things. So we are planning to take some of the research in the graph databases and apply that here.
If you need some point of reference, I work with a colleague also in North Texas who is amazing in terms of graph compression. And if you want the point of contact, I will be pleased to introduce you.
I would love that. I will reach out to you.
Excellent.
Thanks.
So, and I think this is kind of what we intend is there are some intentional overlaps between some of the projects, including some of the other work you do, and this also kind of fits into, with some of the data access, we're very concerned about, whether people know how to find the data, how to access the data. but none of that matters if we don't have integrity, provenance, and authenticity on the underlying data. So some great data stories there.